Hey everyone, Mr. Fransky here. Today we're going to talk about 6.5b in the calculus book, Exponential Growth and Newton's Law of Cooling. Newton's Law of Cooling is one of the neatest things, I think, that we see from differential equations because it really makes sense, and it's a real-world application of differential equations, which is kind of cool. Alright, so let's jump in. So you can probably do these on your own. They're all separable differential equations, but they're really the backbone of what we're going to be doing in this video. So if you want to pause it and try them yourself, you can. Otherwise, we'll do them together. So let's take a look. So we got dy dx equal to 3y. Notice we all have some number times y for all of these, and we're given the initial value, 0 something. So for the first one, I'm going to separate the variables. So I have dy over y is equal to 3 dx. Integrate both sides. We have natural log absolute value of y is equal to maybe 3x plus c. Exponentiate, we have absolute value of y is equal to e to the 3x plus c. That's going to be y is equal to a e to the 3x. And then we can solve for a by using 0, 8. So we have 8 is equal to a e to the 0, so 8 is a, because e to the 0 is 1. So we have y is equal to 8 e to the 3x. Easy. All right, next one, similar idea. dy over 8 over y equal to 8 dx. Integrate both sides. ln absolute y equal to 8x plus c. Exponentiate, absolute y is going to be equal to e to the 8x plus c. That means that y is equal to a e to the 8x. Plug in 0, 10. So we have 10 is equal to a e to the 0. So 10 is a. So y is equal to 10 e to the 8x. Okay, notice there's kind of a pattern happening here, right? We have that principal value or the initial condition right in front, and then we have e to the kx, whatever that is, or ky, sorry, no kx. So this last one, we can separate it again if we want to. dy over y is equal to k dx. Integrate both sides. K is a constant, so we have natural log absolute y equals kx plus c. So we have absolute y equal to e to the kx plus c. So y is equal to a e to the kx. And I tell us 0p is on the function, so then we're going to have y. Sorry, plug in 0, we get p equals a e to the 0, so p is a. So y is equal to p e to the kx. Now this is what's called the general solution for a exponential differential equation. Notice that all these are number times y. You always then will end up with the principal value multiplied by e to the kx. So let's see why this is always exponential growth. So the first thing to notice is that the function is dependent upon itself, right? The derivative of the function is dependent upon itself. There's a function we know that does that, right? The derivative of e to the x is e to the x. So this is somehow going to be exponential because the derivative has the function in it, and there's no other x's along with it. The other way to think about this is if you did a slope field, if it's only y, initially it's going to be pretty shallow, then it's going to be steeper, then it's going to be steeper, and then even steeper, right? The higher you go up, the steeper that slope's going to be. They're going to make exponential functions, right? On the bottom, we have super mellow, steeper, steeper, right? They'd be exponentials going downwards, okay? So we see that if it's only dependent on the y value, that we're just going to have exponential curves. I think there's something else I want to say. Oh, yeah. So in general, I mean, if you want to solve this every time you can, but you can just skip this straight to y equals pe to the kx. And then p is always the what's called the initial condition or initial value, because it's what happens when x is 0. So you have 0 comma p. Sometimes you see it with a y0, so sometimes you see y equals y0 e to the kx. Either way you think about it, whether it's a principal value or an initial value, that's all there is to it. I don't ever memorize this. I just always solve it by separating the variables. But if you want to memorize it, then you don't have to separate the variables every time, which is kind of nice. All right, so chicken Caesar salad and math. So every time I make a chicken Caesar salad, I think about this. I cook up my chicken, and then the chickens will be hot, right? But you can't put the chicken, the hot chicken, into a cold salad because it'll wilt the lettuce. Right, like salad making 101. So what do I do with my chicken? Well, I could leave it sit out in the room, right? But then the coldest it's going to get is room temperature, and it won't cool off very fast, right? What's a way to make it cool off faster? if I put that hot chicken into a cold place, even though I might not want it to go all the way cold, like I don't want it to be super cold, right? But the bigger the difference in the temperature is, the faster the chicken's going to cool off. Okay, so if we were to make a picture or a graph of the chicken, let's say that room temperature is like 70 degrees. So if I leave my chicken sit out, let's say it was cooking in the pan, it's like, I don't know, 150 degrees, something like that. What's going to happen is it's going to cool off, and then it's going to hit an asymptote at room temperature, right? Because if it's sitting in the room, it can't go below room temperature. If the chicken is sitting in the room, it can't go below room temperature. That looks a lot like a exponential with a negative exponent, right? If I put it in the freezer, right, that's what I usually do is I throw it in the freezer. The freezer is a temperature of, like, if we think, I don't know, Celsius maybe. So Celsius, it might be like -5. So then it's going to go from 150, it's going to drop real fast, and eventually it's going to go to -5. I'm not going to let it get there, right? I'll probably take it out like somewhere around here because I don't want it to be too cold, right? But I for sure want, if I have a bigger difference in temperature, then it's going to cool faster. So let's think about that. So bigger difference means it will cool faster. So we're talking about the rate here, right? We're talking about how fast the thing cools. We're not talking about the actual temperature, just how fast it cools. A big difference will make it cool faster. And this is, I think, so cool because Newton realized this. He thought about it in terms of only the rate. He didn't actually think about it in terms of the temperature. He wasn't like, let's know what the temperature is after 5 minutes. He thought, how can I make something cool off faster or heat up faster? And he thought, well, it depends on the difference between the temperature of the thing and the temperature of the surrounding, right? So it's the temperature of the thing. This is the temperature of the object. In my case, chicken. And this is the surrounding temperature. And then, just like we had in the other problems, we need a constant because you're going to have a different rate depending on the different material, right? So like chicken will cool at a different rate than like water, right? If you've taken chemistry, you know water has a very high specific heat. It takes a lot of energy to change the temperature of water. Things like aluminum change energy or change temperature very quickly because they have a low specific heat. That's why like pop is packaged in aluminum cans. But so that constant is going to change depending on what the material is, and then the rate that something cools or heats is going to be dependent upon the difference. If you have a very big difference in temperatures, it will change quickly, right? You have a big rate if you have a big change or a big difference. So let's solve this thing. Okay, so we're going to solve this differential equation if the initial temperature is T sub 0. So that means that when little t is 0, big T is equal to T sub 0, or we could say 0 T sub 0 is on our is going to be on our graph. So we're going to solve this by separation. So I need to get the T with the big T, and the dt is going to come, little dt is going to come over here. So we're going to have d capital T over capital T minus T sub s. Remember, that's a constant. The temperature here is changing though. And that's equal to Ka dt. And this little t over here is time. Now we integrate both sides. Now this is something we're going to see a lot more of, especially when we get to partial fraction decomposition. Integrating this is actually pretty easy. You can do a simple u sub on it if you want to. Capital T minus Ts. Then du is just dt. Because we're just differentiating on this temperature here. And so that means that this turns into integral of du over u, which is just ln absolute u, which is ln absolute t minus ts. So in general, we're going to be able to skip right down to here. Just a natural log of absolute t minus ts, because there's no coefficient in front of the t. If there was, then we would have to do a little bit more. Okay, so this is just ln absolute t minus t sub s. Close that absolute, is equal to kt plus c. Uh-oh. Now we'll exponentiate. So we have t minus ts equal to e to the kt plus c. Now we do the a thing, right? So t minus ts equal to a e to the kt. Now we're going to solve for t. So we add ts to both sides. So we have capital T equal to ts plus a e to the kt. And now we want to solve for a. So we know the initial temperature is T0, so we plug in 0, T0. So T0 is equal to Ts plus a e to the 0. E to the 0 is 1, so a is equal to T0 minus Ts. So this is called Newton's law of cooling. Okay, let's see, we have it up here. T is equal to Ts plus T0 minus Ts e to the kt. There we go. That is Newton's law of cooling. Pretty easy to derive, right? Pretty easy to actually solve this. It's not a real difficult differential equation. But it's something that is nice to have on hand, like for homework problems. AP does not require you to know this. You might have heard last year there was a question about a potato that had to do with a cooling potato, but they expected you to solve the differential equation. You never had to know Newton's law of cooling. I think that people actually got in trouble because they thought they had to memorize Newton's law of cooling when they saw this problem, and you don't. You just solve it like you solve every other differential equation, and you end up with something that looks like this. So, the constant, notice here, the constant has to do with the difference between the initial temperature of the object and the temperature of the surroundings. So again, if you have a big change here, you're going to have big changes in the function. That's why that constant depends on the difference between the initial temperature and the temperature of the surroundings. That's why I put my hot chicken into a very cold freezer, because I want the temperature of the surroundings to be very different. That'll change the temperature quickly. Notice the temperature of the surroundings is added over here. So as t goes to infinity, generally k is going to be a negative number, because if things are cooling, they're going to be dropping off. So that plus ts here, that's going to give you a horizontal asymptote, because that's where it's going to stop. Whether it's coming up and heating up or coming down and cooling down, that's going to be your kind of equilibrium point. That's where it's going to stop, right? It can't go below or above that temperature of the surrounding. That's where it's going to kind of stop. Okay, so let's do a problem with this. So I'm going to rewrite that. T is Ts plus T0 minus Ts times e to the kt. Alright, so a body is found at 9 a.m. in a 68-degree room. That sounds like Ts. 68 degrees. That's our temperature of our surroundings. It's 90.3 degrees. An hour later, it's 89 degrees. So we have an initial time, or initial temperature. So let's say that T0, the initial time, T0 is at 9 a.m. Okay, so then T0, big T0, is 90.3 degrees. Okay, an hour later, so T of 1. So 1 hour later, it's 89 degrees. When did the murder occur? So notice what we do. Let's see what we know here. We know Ts, we know T0, we know T, we don't know K. So often with problems like this, you have to find K first, and then you use it somehow. Okay, so we found this dead body at 9 a.m. It's in a 68-degree room. It's 90.3 degrees. Okay, let's put in all the pieces that we know. So you have 68 plus 90.3 minus 68. E, I don't know K, times 0. Okay, and that is equal to, hold up, let me think about this. Yes. Yeah, that's what we want. An hour later, it's 89 degrees. Yeah, so we're going to use the 89. Sorry. That's what we want. So K times 1. And let's say, using the 0 isn't helpful, right? If we put the 0 in here, we're going to end up just with 90.3, right? Because that's the initial temperature. All right, so we know it's 89 degrees after an hour. So when T is 1, we have our initial temperature minus the temperature of our surroundings, plus the temperature of the surroundings is equal to our current temperature, which is 89. Now we have to solve for K. So this is why you dealt with logs and exponents in pre-calc, because we have to be able to solve equations like this. So you subtract 68, so we'll probably do that, it's 21, right? So 21 is equal to 90.3 minus 68. Let's see, 78, 88, 22.3. Hope I did that right. E to the K. Divide both sides by 22.3. Okay, and then we have e to the K equals this, so E is going to, K is going to be equal to undo this, we have to do natural log. So natural log of 21 over 22.3. Okay, I'm going to go to a calculator for that. I think I've got it ready to go here somewhere. I hope so. There we go. Okay, so we're doing natural log of 21 over 22.3. Gives us, as we suspected, a negative K value. Okay, so you want to use as many decimal places as you can for this, because we haven't solved the problem yet, right? We're going to use this in our solution. So I'm actually going to leave it in my calculator and grab it later. But for now, we can just write it's negative 0.060064. Okay, so we have our K. So now our formula, our overall formula is T is equal to TS, which is 68, plus T0 was 90.3. That's when the body was found, minus 68 e to the negative 0.060064 t. Now they want to know when the murder occurred. Well, when the murder occurred, what was the temperature of the body? Well, a live body is how hot? 98.6 degrees, right? So we have 98.6 equal to 68 plus 90.3 minus 68. I suppose we can actually plug that in. It's 22.3. E to the negative 0.060064 t. Now we're solving for t. So 98.6 minus 68, that is 30.6, equal to 22.3 e to the negative 0.06 t. I'll drop off those decimals. Divide by 22.3. Okay, and then natural log, and then divide by 0.06, negative 0.06, excuse me. So t, a little bit of algebra, I'm going to skip a couple steps here. It's going to be natural log 30.6 over 22.3 divided by negative 0.06. Well, our k value, 0064, right? Okay, let's go back to the calculator. Oh, I can almost see it. So it's ln of 30.6 divided by 22.3, and then we divide by, negative, so I'm actually going to go up and grab my k value. Gives me an answer of negative 5.267. Now let's think what that means. It's a negative time. So that's the time before 9 a.m. that the murder occurred. That makes sense to me that, it was hotter earlier, right, because it's been cooling off. So negative 5.267, so that's 5 hours before 9 a.m. So it's like between 3 and 4 a.m. somewhere, 5 1/4, so that's about 3:45. This is how they use it in forensics. This is what they do. They measure the temperature of a body, measure it an hour or so later. Any number of hours later will tell you. You'll be able to solve for K. And then you can do a little bit of algebra using logs to be able to figure out when that person actually died, which is kind of cool. Nice. Okay, Newton's law of cooling, math in action. Love it. All right, let's see what else we got. Population y grows according to dy dt equals ky, where k is a constant, so we know it's going to be exponential. And that makes sense, right? Populations grow exponentially. T is in years. The population doubles every 10 years. Find k correct to 3 decimal places to the right of the decimal. So we're looking for k. So we know the solution to this is going to be y equals p e to the kt. P e to the k, t in this case, because we have dy dt. All right. So now they tell us that it doubles every 10 years. So when t is 10, so e to the k times 10, what's it equal to? Well, if we started with p, what do we have now? We got 2p. I love problems like this because you can just divide both sides by p, and they just cancel. So what we said was we know it doubles every 10 years. So if we started at p, we now have 2p. So now we can take natural log of both sides. So we have 10k is equal to ln of 2, and then just divide by 10. All right. Go back to our calculator. ln of 2 divided by 10. ln of 2 divided by 10 gives us 0.069315. Has to be 3 places correct. I have even more. Excellent. I had to switch my calculator app, so I'm probably not on float like I should be, but I'm still getting at least 3 decimal places, which is good. All right, I think I got one more. Puppy weighs, who doesn't like puppies? Puppy weighs 2 pounds at birth. That sounds like an initial value, 0.2. And 3.5 pounds 2 months later, 3.5. If the weight of the puppy during its first 6 months is increasing at a rate proportional to its weight, how much will the puppy weigh when it is 3 months old? So they're telling us here, increasing at a rate proportional to its weight. That means that the change in weight with respect to time is proportional to its weight, so it's kW. So we have a exponential formula here, which makes sense because weight often, for at least the beginning of your life, is an exponential growth. So that means W is going to be equal to P e to the kt. Right? We don't have to actually solve it because it's the same every time. So we're going to plug in what we know. We know we have 0, 2, so P is going to be 2. W is 2e to the kt. They tell us it's 3.5 pounds 2 months later. So it's 3.5 pounds when T equals 2. So now I can solve for K. Divide both sides by 2. Natural log, and then divide by 2. So K, well, let's take that a little slower. So we have 2K is going to be equal to natural log of 3.5 over 2. And then we divide by 2. To our calculator. Oh, come on. And let's see. We got natural log of 3.5 over 2. And then we're going to divide that by 2. 0.279808. So that's our K. Now what are they actually asking? How much will the puppy weigh when it was 3 months old? So W of 3 is going to be 2e to the 0.279 times 3. Which is, let's see. So we have 2e, have to get e over here by the pi, to the power 0.279808 times 3 gives me 4.63 pounds. Not too bad. Alright, that's all I got for exponential functions. Hope you learned something. Love you guys. That's why I'm here. Have a great day.